Okay, so good afternoon. It's Monday afternoon. We are just going, I'm just going to go over some of the real easy basics of waves. Like I said in class, we are done with mechanics for a little while. We're going to hit waves, we're going to hit electrostatics, we're going to hit circuits, then we're going to come back and look at another part of mechanics that you have never studied before. That'll take us pretty close to the AP test. We'll squeeze in gravitation, we'll call it a year. So we're coming down the home stretch. Waves, okay? We're going to just go over wave basics today. The reason I'm doing this is just, again, trying to save a class period or two so that we can get more in and so you guys can be a little bit more prepared for the exam. So a wave, it's good that we just studied simple harmonic oscillation because that's all a wave is. A wave is simply a type of oscillation . And it's a type of oscillation in which you take energy that's in one location and you transfer it to another location. Okay, it's all about energy transfer. A type of oscillation in which energy is transferred from one point to another. Type of oscillation in which energy is transferred from one point to another. This is different from transporting matter. I mean, transporting matter is like me picking up a basketball and bringing it somewhere and setting it down. Okay? That is not what a wave does. A wave does not transport matter, it transports pure energy. Last year, you studied two different types of waves. We studied mechanical waves. So actually, let me backtrack on what I just said. Mechanical waves are waves in which matter and energy are transferred by the wave. So I guess it's not so much of a backtracking as it is a clarification. Matter still is not transported from one place to another. It is moved around by a mechanical wave, but it is not necessarily brought from the wave's origin to where the wave ends up. Okay? Matter might be jostled around a little bit, might be jiggled, might be oscillated, but it usually does not flow with the wave itself. The energy is what moves from place to place, from where the wave starts to where it ends up. The matter does move, but it's more of a back and forth motion than anything. So a mechanical wave, this is specifically for mechanical waves. Mechanical wave is a wave in which matter and energy are transferred by the wave. Any mechanical wave requires what we call a medium. A medium is just a fancy word for material, or an even less fancy word. A medium is just something to move through. Which sounds kind of silly. Well, obviously there's got to be something. The lack of something would just be nothing, and in physics we call that a vacuum. So it is important that we say that it is a material, it is something to move through. Mechanical waves can't go through nothing, they can't go through a vacuum. Okay? Vacuum is not allowed. Okay. Vacuums are not allowed. Not your, cleaning vacuum, but a vacuum meaning absolutely no matter in an area whatsoever. That is a vacuum. Some examples of mechanical waves. Okay. You are pretty familiar with mechanical waves. You see them very frequently. Water is an example of a mechanical wave. Seismic waves, some kinds of seismic waves, well, no, all kinds of seismic waves are mechanical waves. Water waves, I should say. Seismic waves. And the most important ones that we will study in this class, we touched on them last year, but this year we're going to do a lot with them, are sound waves. I want you to underline that. Sound waves are going to be the toughest part of this unit. Not necessarily because the matter, the topic is hard, but it does go pretty in depth with sound waves. And when I first really learned how to teach this, this became one of my favorite lessons to do, because it's an interesting mathematical derivation and it's a really, really neat result. I wish we had more time to do labs with this. We don't really have time to do labs with this, unfortunately, but this was one of my favorite things that I learned. It was very, very interesting. And I honestly think that I learned it better in teaching it last year and the year before than I did ever in college or in high school myself. So I'm really excited about this stuff. Another type of wave that you will see, other than mechanical wave, is an electromagnetic wave. An electromagnetic wave is different from a mechanical wave in that only energy is transferred. This type of wave does not necessarily move matter. It doesn't have to. It can interact with matter, but it doesn't move, it doesn't jiggle around matter necessarily. It can get transmitted without matter. And if you think about it, that kind of means it can get transmitted without a medium. In other words, it can go through a vacuum, which is very good news for us. The reason it's very good news for us is because electromagnetic waves are how the sun gets energy to us. Okay? That's how we get energy from the sun, through electromagnetic radiation. There's nothing between the Earth and the sun. Whole lot of vacuum, whole lot of empty space. If sunlight was a mechanical wave, it would not be able to go through that vacuum. It wouldn't be able to go through that empty space. We would not get the energy from the sun. Thankfully, it is an electromagnetic wave, so it can transfer through a vacuum. There is no medium required. Now, moving on to a little bit about electromagnetic waves. What an electromagnetic wave really is, it tells you in the name, electro and magnetic. It is simply a combination, I say simply, it is a combination of oscillating electric and magnetic fields. I'll give you the examples and then we'll go back to that statement. The examples are just the electromagnetic spectrum that you studied last year to some extent. We started with radio waves. We had microwaves in there, not the kind you cook with, the kind you, the radiation. We had, let's see, infrared, visible light, which is the one I'll talk about in just a second. After visible light comes ultraviolet. Okay, X-rays and gamma rays. So this is interesting. Okay, let's go back to that combination of oscillating electric and magnetic fields. One type of electromagnetic wave is visible light. The light that you are using, that you use to see, that hits your eyes and your brain interprets that. It is always shocking to me when I step back and think that the reason that you are able to see all these things around you are because your brain is interpreting and oscillating a changing electric and magnetic field bouncing off of some other object. And that light, that change in electric and magnetic field is coming straight to your eyes. When you think about it like that, it's like, you know, all these colors are just, they just mean, all they are, they just mean how quickly are these electric and magnetic fields oscillating, okay? And how much are they changing? People like to depict light as a transverse wave like this, which it is a transverse wave, okay. But the thing that's oscillating, nothing is actually moving up and down. This is the graph of how the electric field and the magnetic field are changing over time. Every time I think of that, it blows my mind. That the fact that we can see is because we are interpreting the strength, the changing strength of an electric and magnetic field. It's really, really remarkable to think about it in those terms. Anyways, I'll stop geeking out. Electromagnetic radiation, electromagnetic waves are different from mechanical waves. So that's a little bit about the types of waves. We have to talk about their shape. So I'm going to erase this and talk real quick about their shape. The shape of these waves. We have two basic shapes. We'll split the paper. We have transverse and we have longitudinal. Not longitudinal, longitudinal. There we go. Longitudinal. So, transverse wave is the shape of wave that you are used to. You see a transverse wave like this. Okay? It's a classic wave shape. Let's say that the wave is traveling in this direction. Direction of wave travel. And what distinguishes a transverse wave from a longitudinal wave is that if you were to take a little tiny piece of that wave, it's known as a wave element, okay? And you were to categorize its displacement over time. And I can demonstrate this for you in class if you really need me to. Hopefully most of you remember this from last year, or you picked this up in another science class. This little point on the wave, as the wave travels this way, this little point does nothing more than move up and down. It oscillates like this. As this wave passes, so let's see, this little point, this part of the wave, imagine this is like a rope, and there's a bunch of waves on this rope. This little point is about to go into what we call a trough on the wave. So it's going to move down. But then, the crest of the next pulse comes along, and this little part will move back up. Okay? So there's this wave element, the displacement of the wave element ends up being up and down. The wave's moving to the right. That means the displacement of the wave element is perpendicular to the direction of the wave's travel. It's perpendicular to the direction of the wave's travel. And the important type of wave that moves, that is a transverse wave, light waves are transverse. Light waves are transverse. On the other hand, longitudinal waves. Your example, so before for transverse, your example was kind of like a rope that you can imagine, like a jump rope. It's got wave pulses in it. The example for a longitudinal wave is a slinky, moving in a particular way. Okay, so might be kind of tough to tell on there, but I have a slinky here that has certain regions where it is very compressed. That undergoes compression here and here because you can tell that the coils are closer together. And in some other places it undergoes elongation. The coils are more stretched out. Okay? This would be if like you took a slinky and you stretched it out with a buddy, and then what you did was you took the end of the slinky and you just push it. Okay? You push the end of the slinky towards your friend. It would compress the slinky in some spots, and that compression would travel down the slinky. And then behind it, as you remove the push, you would have a more stretched out region called the elongation. So this would happen if you really like pushed it a couple times and you sent these pulses. That's what a wave is called when it's just like one little change in a wave's motion. It's a pulse. That's what these are called as it travels down. So like here's a pulse, here's another pulse. Okay. Now, the parts of the slinky that move in this case, if you imagine a little piece of the slinky right here, that part of the slinky is not going to end up all the way down there at the other end of the slinky. Instead, when it compresses, it's going to move a certain way. When it elongates, it's going to move a different way. This little piece of the slinky is simply going to move back and forth. Okay? Matter of fact, every part of the slinky moves back and forth parallel to the wave. There is a whole bunch of different parts that will move. That one's a little crooked, I don't like that. Back and forth like this. Hopefully you can see how that's, different from a transverse wave. As the direction, I should say, of wave travel is in this direction. As the wave moves to the right, the slinky oscillates parallel to that. Okay? The displacement of this matter is parallel to the direction of wave travel. It is parallel. The wave that undergoes longitudinal motion, that has a longitudinal shape, that for us is sound waves. Sound waves are longitudinal. The reason sound waves are longitudinal is because the way a sound wave works is a sound is made by pressure differences in the air. So as I'm talking to you, my throat is moving and it's causing pressure differences in the air that propagate out of my mouth and towards, well, in this case the camera, normally towards you guys as you're sitting in my room. And then your eardrum recognizes those changes in pressure and it interprets that as sound. So sound waves are longitudinal because the pressure waves that I'm talking about are little tiny air molecules that are getting basically knocked around in the air. Okay? In order for the wave to propagate, in order for it to move, propagate just means move, I need to displace, or the sound wave needs to displace matter to propagate, to move, to spread. And so if it needs to displace matter in order to spread, well then you need a medium. You can't have a vacuum. Okay? So you need a medium. This is why there is no sound in space, because there is no medium for the sound wave to propagate. There is no pressure difference because there is no atmosphere, there is no matter in order for there to be a pressure wave, in order for there to be spaces where there's lots of compression, lots of air packed together, and then it's actually called rarefaction, I think.